On the left is our diene. This is cyclopentadiene, and we have this bridging CH2 to think about. On the right is our dienephile, and we have these two aldehydes that are cis to each other. So in this video, we have stereochemistry for the diene and the dienephile, and we're also going to talk about the endo and exo products. But first, let's just think about our Diels-Alder reaction without any stereochemistry. So we're going to move our 6 pi electrons around. Take these pi electrons and we're going to move them into here to form a bond between these two carbons. These pi electrons are going to form a bond between these two carbons, and finally these pi electrons are going to move down. So if we draw the product, again not worrying about stereochemistry, we put our double bond in here, and in these aldehydes I'm going to abbreviate as CHO. So we have CHO and then another aldehyde down here, so CHO. We can put in our bridging CH2, so I'll just draw that in. And let's follow our pi electrons. So our pi electrons in red formed a bond here. Our pi electrons in blue formed this bond. And our pi electrons in magenta formed this bond. But notice for our product, we haven't really shown any stereochemistry. So where are these aldehydes in space? How do they relate to this bridging CH2? Well, let's say the diene and the dienephile approach each other in this way. So we know that a bond forms here, so this bond in red, so that's a bond that forms between this carbon and this carbon. So that bond forms in here. And for the product, here you can see that bond. And then we also have this bond in blue, which forms between this carbon and this carbon. So it's a bond that forms in here, and here is that bond on our product. We need to think about the stereochemistry of the diene first. So we look at our cyclopentadiene, and we have this bridging CH2. We know that inside substituents go up. So on our model set, here's that CH2, and here are the bonds that are leading to it. And when we form our product, that CH2 goes up in space. Next, we need to think about the stereochem of our dienephile. So we have a double bond, we have hydrogens on the left side, and if we draw a line here, we saw how to deal with this in earlier videos. The stuff on the left side goes down. So these hydrogens, if we follow them along, so here are the hydrogens, and we can see them in our final product. If we're staring at the final product in this direction, those hydrogens are going away from us in space. So the hydrogens would be down. And these aldehydes here, so these aldehydes I've made red in the model set. So here you can see the red, which is just standing in for our aldehyde. And those aldehydes end up on the same side. And if we're staring down this way, here are the aldehydes. Those are actually coming out at us. So when we draw in our product, let's go ahead and start drawing this in here. We'd have a bicyclic compound, so we'd sketch that in. And we have our bridging CH2, so let's put that in. We have our double bond here. And then we have our aldehydes. Our aldehydes are up. So at this carbon, we need to draw in an aldehyde up, so CHO. We have a hydrogen that's down, so let's put in our hydrogen going down at this carbon. And then we have at this carbon an aldehyde going up, so CHO, and then a hydrogen going down. So this is the exo product. So this is said to be the exo product because we have our aldehydes up, our bridging CH2 is up, and then here is our double bond. So that's one of the possible products. What about if our dienephile approaches in this direction? So if we have our hydrogens here on our double bond and we draw a line, we know the stuff on the right side of the double bond ends up. So here are the two hydrogens, and when those two bonds form right in here, these hydrogens are up if you're staring down this way. The stuff on the left side of the double bond, now our aldehydes are on the left side. So here are the aldehydes, and when our product is formed, we're looking this way. The aldehydes are going away from us in space. So the aldehydes are down. Let's draw in this product. So we have our bicyclic. Let me go ahead and draw that in here. So here's our bicyclic with our bridging CH2. Our double bond is in the back. And now when we're drawing these in, the hydrogens are up. So at this carbon, there's a hydrogen up, and then there's an aldehyde going down. So here is our CHO going down. Same thing at this carbon. So a hydrogen's going up, and an aldehyde is going down. This is called the endo product. So let me write that in here. So this is endo. Our aldehydes are going down, our bridging CH2 is up, and here is our double bond. It turns out the endo product is the preferred product most of the time. And this is called the Endo Rule, or the Alder Endo Rule, and it's thought to be due to an interaction between the developing pi bond, which occurs between these two carbons, and the carbonyl groups, so the carbonyl groups for our aldehyde here. And even though I didn't put in the carbonyls, we know that these red spheres here symbolize those aldehydes. And so there's an interaction between the developing pi bond and those carbonyls, which stabilizes the dienophile approaching in this way. And that gives us our aldehydes down in space. That gives us our endo product. So the endo product is preferred. With the exo product, these carbonyls, these aldehydes would be way out here. That's too far away from the developing pi bond, so there's no interaction. So the exo product is not preferred. Let's do one more problem. On the left is our diene, on the right is our dienophile. And let's draw the product without stereochemistry again. So we move our 6 pi electrons. So we form a bond between those two carbons, we form a bond between these two carbons, and these pi electrons move down. So if we draw in our product, again not worrying about stereochemistry, we'd have our aldehyde coming off of this carbon, we'd have a methyl group here and a methyl group here. Following our electrons in red, these pi electrons formed this bond. Our pi electrons in blue formed this bond, and our pi electrons in magenta moved down to here. So let's highlight those bonds on the model set, on the picture. So this bond in red formed between this carbon and this carbon. So formed in here. So there's that bond on our final product. The bond in blue formed between this carbon and this carbon. So here's that bond on our final product. But notice, if we draw the dienophile approaching this way, there is no stabilizing interaction between the developing pi bond and the carbonyl groups. So down here, I've flipped over the dienophile, so it has an endo approach to the diene. And now we think about our stereochemistry. So let's worry about the stereochemistry of our diene first. We know that inside substituents go up. So these two hydrogens, here they are on the diene, and in our product, those two hydrogens are going up in space if we're looking down in this direction. So those methyl groups, so let me change colors here. So these two methyl groups, which I've used yellow in the model set, those two methyl groups go down. So down relative to those hydrogens going up. So those methyl groups are going down if we're staring down this direction. So let's draw that in for our product. We have our ring, so let's put in our double bond, and those methyl groups are going away from us. So we put those on a dash. So there's one methyl group and there's the other one. Next, let's think about the dienophile. So here is our dienophile, and if I draw a line here, we know the stuff to the left ends up down. So this aldehyde is going to be down in space. So let's follow that aldehyde through. So here is the aldehyde. We know that this endo approach gives us some stabilization between the developing pi bond and our carbonyl. So for our product, here is the aldehyde. And again, if we're looking down, this aldehyde is going away from us in space. So we'd have to put that aldehyde on a dash. So here is the aldehyde going away from us in space. What if the dienophile approached this way? Well, this is still an endo approach, because here would be our aldehyde and our developing pi bond would be back here, so there's a stabilizing interaction. So here's the aldehyde in our product, and if we're staring down this way, this aldehyde is going away from us in space. So let's draw this product. We would have our ring, we would have our double bond, and aldehyde's going away from us at this carbon, so we put that aldehyde on a dash. And our methyl groups are still going away from us. So this one's going down and this one's going down. So we draw in our methyl groups. What is the relationship between these two molecules? Well, they are enantiomers of each other. So you should get a pair of enantiomers.